All right, welcome to The Explainer. Today, we're diving into a really radical new scientific idea. What if our world has a physical memory? And what if it was built by the tiniest living things on the planet?
Okay, so let's just jump right into this. What if the past isn't actually gone? What if it's literally written into the very soil and water all around us? It's a pretty wild thought, right? But a new theory is proposing just that. That for billions of years, trillions of ancient microbes have been acting like these tiny, invisible architects, and they've left behind this hidden layer of reality that physically shapes the world we see today. So let's start with this mystery. A hidden layer of reality. Could there really be this persistent physical history of life that's still influencing everything? I'm talking about things like how water flows, or even how chemical reactions happen, right here, right now. Okay, so how do you even begin to investigate something like that? Well, scientists are basically following a trail of breadcrumbs, a series of clues. And what's really cool is that these clues are found across vastly different scales. I mean, from entire landscapes you can see from a plane, all the way down to what's happening inside a single tiny bacterial cell. So clue number one, the landscape scale. Let's start big. For years, we've known about these gangs called biocrusts. You can think of them as this living skin that forms on top of soil made up of microbial communities. And they have a huge effect on the world around them. They can totally change how porous the soil is, how water runs off, and even prevent erosion. It's a super clear example of microbes literally re-engineering their environment on a massive scale. All right, now let's zoom in a bit. Clue number two, the biofilm scale. If you look really close at microbial colonies, biofilms, you see something incredible. These bacteria aren't just sitting there in some random blob. Nope, they're actually building these intricate little channels and tunnels. They're basically microscopic highways designed to move nutrients around faster. And then there's clue number three, the subcellular scale. And this was the real shocker. A pretty recent discovery, using some super advanced imaging, found that microbes are building these long, functional, spiral-shaped tubes inside their own cell walls. I mean, think about that. We're seeing the same pattern of building at every single scale. Which, it really begs the question. What if all these clues are connected? What if it's not a coincidence? Well, that is exactly where this new theory comes in. It proposes a single, unifying idea that ties it all together: the material memory field. So what is the material memory field? It's basically a way to take this kind of vague, poetic idea of ecological memory and turn it from just a metaphor into something real and measurable, a physical parameter you can actually plug into the equations of physics. It quantifies the historical imprint, all those tubes, fibers, and crusts that microbes have left behind over billions of years. The core idea is actually pretty simple to break down. You can think of it like this: the past writes, and the present reads. So over all that time, microbes have physically written a structure into the environment. That's the memory. And today, things like water flowing or chemicals reacting, they have to read that memory. They have to navigate this pre-existing architecture. It's a really simple concept, but it has absolutely profound effects. Okay, but a really powerful theory has to do more than just sound cool, right? It has to be testable. It has to make specific predictions that you can go out and try to prove wrong. And this one does. It makes three very specific, testable predictions. So how do we test it? Well, here are the three predictions. First, they call it creating fast lanes. The idea is that particles should travel way faster along the direction of these microbial tubes, like cars on a highway, than trying to go across them. Second, finding the right rhythm. This one's wild. It predicts that a specific frequency of gentle vibration should actually make chemical reactions inside these structures more efficient. It's like finding a resonant sweet spot. And third, building protective shields. The theory says the very shape of these tubes should physically shield sensitive molecules inside from getting damaged by chemicals on the outside. And get this isn't just some abstract theory. Researchers have already laid out a concrete 8 to 10 week experimental plan to build these very structures in the lab and test these exact predictions. So they can actually go out and verify these claims, connecting the dots all the way from those tiny little helices inside a cell in a lab gel to how water soaks into a real plot of soil. All right, so let's say they test it and it holds up. The big question is, so what? What does this all mean for us? If we can actually understand and even harness this microbial memory, what's the payoff?
Well, it really gives us two powerful things: brand new knowledge and brand new tools. For knowledge, we get this profound new way of understanding our planet. We can finally link the architecture inside one tiny cell directly to how water moves across an entire landscape. It's a whole new way to measure ecological history. And for tools, we could potentially design smart compartments to make green technologies way more efficient, or learn how to better manage those biocrusts to control the risk of soil erosion. Super practical stuff. And this really gets to the heart of it. This whole framework turns ecological memory from just a nice metaphor into a real, measurable parameter. It gives us a language, a set of tools to describe how the deep, deep past of microscopic life is still an active force, shaping the world we all experience every single day. So that leaves us with this final, really provocative thought to chew on. If it's true that microbes are literally writing history into the soil, what other planetary memories are out there? What else is written into the very fabric of our worlds, just waiting for us to figure out how to read it?